Hello and welcome to this video about large signal diode impedance. This is a video that investigates what a large signal diode impedance would look like for diodes that are used in rectifiers and AC electricity. In this video, which is part 3 in the series, we'll be looking at multi-frequency impedance. That is, an impedance for a diode where the voltage waveform is expressed in a long list of cosine and sine functions as shown. A0 would represent the amount of DC or constant voltage, and A1 and B1 represent the amplitude of the fundamental sinusoid or harmonic, and by how much it is phase shifted. And the other A's and B's represent the amplitude of higher order sinusoids and by how much they are phase shifted. This can be represented as a column vector as shown, and the length of this vector can grow to any theoretical size, but computers tend to slow down a lot when they are 50 elements long. Here are the multi-frequency impedances of inductors and capacitors, corresponding to this type of voltage vector. It is noticeable that any of the particular frequencies don't mix with other frequencies, and the arrangement is consistent with the use of complex numbers. In the last column, I calculated the sine of the highest frequency in terms of the other frequencies, because I only had the cosine term for the highest frequency, since this is a square matrix with even rows and columns. And here are the corresponding admittances. They are really just the impedances swapped with each other. These are what we'll put into the circuit solving matrix. And here are the two time-sampled impedances for the two types of diodes used in the bridge rectifier circuit. You'll have to look at part 1 of this series to see how I calculated them. They function as a timed switch for the circuit. And here are their corresponding admittances. These are just the inverse of the impedances, and it is easily done because they are diagonal matrices. And here is the fast Fourier transform matrix. It transforms a time-sampled vector into a multi-frequency vector. It performs a Fourier transform on a sample of points in time very quickly. And here it is again in a more simplified form. And here it is evaluated for an 8 by 8 matrix, and its inverse is calculated too, which can turn a multi-frequency vector back into a time-sampled vector. And so here's a bit of theory. The multi-frequency diode admittance, YDW, is equal to this expression. To explain it, we'll multiply it by a multi-frequency voltage vector denoted by V with W in brackets. The first matrix F, which is a fast Fourier transform matrix, turns VW into a time-sampled voltage vector denoted by V with T in brackets. So then the time-sampled diode admittance, YDT, can easily operate on it, turning it into its corresponding time-sampled current vector. Then the inverse fast Fourier transform matrix turns the time-sampled current vector into its corresponding multi-frequency current vector. So now we have a series of matrix operations that can operate as a multi-frequency diode admittance. But because matrices obey the law of associativity of multiplication, we can multiply all these three matrices together into one matrix first, before multiplying it by the multi-frequency voltage vector, and therefore this is its multi-frequency admittance. Performing this operation gives us these two multi-frequency diode impedances, which represent the two types of diode in the bridge rectifier. They don't look as messy for an 8 by 8 matrix as for most other matrices, But there is a lot of frequency mixing, and this sort of matrix can't in any way be represented by a complex number or even a list of them, and it's only an approximation anyway. And here are the two corresponding diode admittance matrices that we'll be putting into the circuit matrix so as to solve the circuit. And it should be pointed out that the impedance of a resistor is almost always the resistance multiplied by the right size of identity matrix. There might be occasions when this isn't true. It's easy to see why this should always be true. Here is a graph of the standard input we'll be using, which is a sine function, which is the standard input for a rectifier. Although its phase can vary, it can be thought of as a universal input for the purposes of this simulation. Here is the output for a bridge rectifier circuit across the load resistor and capacitor. It looks like it has near zero ripple. I've decided to display this voltage as a function of time rather than a function of frequency, so as to better see and understand the output. I did this despite having used multi-frequency vectors in the main calculations. And here is the voltage across one of the diodes. It looks like it is a perfect sinusoid. Here is the output voltage for a half-wave rectifier in series with an inductor. It looks like a DC voltage with near zero ripple as well. And here is the voltage across the diode. It has a bit of ripple in it. And here is the voltage across the inductor. It looks like the ripple from both of these elements cancel each other out, so that they don't affect the output voltage. And here are the waveforms for a half-wave rectifier with a larger inductance. The ripple is larger, but the output voltage is unaffected by this ripple, even though it has changed in amplitude. So I hope that this video has been helpful for you in your quest to study large signal diode impedances.